Welcome, everybody, to part 5 of a 6-part marathon. I'm doing a full 12-hour marathon. This is a presentation by PhD Tony on gravity, and I'll let him introduce the full topic and everything. But I'm recording this for the podcast, so I'm going to do the intro. Then he'll do the thing, and then the ending of the podcast, and then we'll interact. We'll talk with the live chat and stuff. So don't get confused. I'm not actually wrapping it up. It's a fake out. So, all right. Welcome, everybody, to the Toon Show. We'd like to discuss smart science topics. And today I've got the Smarty Pants science presenter, PhD Tony, who will be discussing with us the history of the measurements of gravity. I'll let him explain the entire topic, the whole description of it, and but do make sure that you tell us your history and your background too. So anyway, PhD Tony.
Hi, Toon. You're going to have to let me share my screen.
Oh, certainly.
For when I start, my name's Tony. I'm a geophysicist. What I work on at the moment is modeling satellite orbits for satellite gravimetry missions. And what I'm hoping to do today is just present a little of the lesser known history of our studies of gravity and how we know what we know. So I might try sharing my screen again and see if...
Should be able to now.
Yep. Okay, so can you see that?
I can, yes.
Okay, so
there's some overlays in front of it.
All right, we'll get rid of those.
There we go.
So the earliest investigations of gravity were by Galileo, who did a series of investigations of balls rolling down ramps, and determined that the distance that they traveled was proportional to the square of the time. And he also did some demonstrations of with falling objects, though one of the most famous that he's supposed to have done, he didn't actually do, which was dropping balls from the top of the Leaning Tower of Pisa. Never happened. But in order to measure gravity precisely, the first time this started was actually with pendulums. It turns out that if you've got a pendulum with a rigid rod, the period of the pendulum is given by this formula down the bottom here. The period is about 2 pi times the square root of the length of the rod divided by gravitational acceleration. Now, this can be used, if you've got accurate clocks, to work out what the value of gravitation is. Now, that's only an approximate formula. In practice, there are things like turbulence effects, buoyancy effects, the aerodynamics of the rod and the weight. There are small terms that offset this, but over time, people developed more and more accurate pendula for the purposes of determining the value of gravity. This formula, incidentally, was determined by a chap named Christian Huygens, whose name you may remember from optics.
Yep.
And he built some instruments to carefully measure gravity, but they stopped working when they were taken on board a ship, and he was very unhappy about it. But the guy who took them on the ship and didn't start them up again, he went on to actually prove that in Cayenne, the capital of Guyana, of French Guyana, gravity was different from what it was in Paris, and quite significant. And he did like 10 months of observation. So this was the first evidence we really had that acceleration due to gravity varies from location to location, that if you go from one point to another. I should also say that if you feel like I should clarify anything a bit more than I have, please feel free to intervene and ask questions and that sort of thing. Shortly after this, people were still dealing with Newton's Principia Mathematica, and there was a scientific controversy about whether or not the Earth was prolate, sort of egg-shaped, or oblate, which is sort of more flattened. The Cassinis, a family of famous French astronomers, thought that they had observational evidence that the Earth was prolate. Newton and all of his followers thought that actually the Earth should be oblate. So they decided that what they would do was go to different latitudes and measure a degree of latitude. How long is the degree of latitude? Is this distance longer at the equator, or is it longer at the pole? And by degree of latitude, we mean change in elevation to fixed celestial objects. In order for that to change by a degree, where do we have to go? So for the prolate, latitude is longer at the equator and shorter at the poles. For oblate, it's the other way around. So this was the experiment that they set up, and they set out two expeditions. One to Lapland with Celsius. Yeah, that's Celsius, and a guy called Maupertuis. But the one that we're more interested in is the one that went to Ecuador, which was led by a guy named Bouguer, famous for the Bouguer gravity anomaly, and Charles de la Condamine. Here are their pictures. The expedition was run by Louis Gaudin, who is famous for nearly bankrupting the expedition by lavish spending on prostitutes in the Caribbean. They needed to get the expedition refinanced because he'd spent all of its money. That's one of the things that the expedition is famous for. The other one is this woman, Isabelle Gaudin Desordonnées, who ended up traveling from Ecuador over the Andes and down through the Amazon in order to match up with her husband, a journey that only she survived out of her entire party of 30 odd people. And she was eventually found alone, wandering barefoot. So it's as you can see, it's been the subject of a number of books, and it's a really, really sort of engaging.
What did they die of?
Various different things. Many of them died of disease. Some of them died of starvation. Some of them seem to have been attacked by local natives. But she was one of them. One of her ladies in waiting, her most loyal one, just wandered off into the forest to die. So there were a variety of causes. But anyway, it's a remarkable story, well worth reading up on. And as you can see, there are multiple books there. But the main scientific business that they wanted to do was to lay out a surveying course between Quito in the north and Cuenca in the south. Here are some maps of the surveying plots that they did. A combination of really severe topography and really harsh weather meant that a project that was supposed to take them 10 months ended up taking 10 years before they could return. So they had a lot of time to kill. And Bouguer made some observations on Mount Chimborazo, and he noted that his plumb bob seemed to be deflected towards the mountain of 7 arc seconds. And he guessed that this might be due to gravity, but it was a new theory to him, and his calculations were wrong as it happened. The next major development was the surveying of the Mason-Dixon line. which had a lot of systematic errors in it. And we'll get on to those in a bit. But Henry Cavendish suggested that what was happening, Henry Cavendish of the experiment fame, what he imagined was that the Allegheny Mountains were having a deflective effect on plumb bobs and on levels that was throwing their resources out. So what do I mean by systematic errors? There are two ways you can work out where you are on Earth's surface, or where a point is. You can do it by surveying with reference to a network of surveying stations, or you can do it by looking at the stars. It makes sense if you're looking at a celestial object with a given altitude at a particular, as it passes across its azimuth, that should tell you what your latitude is on Earth. But the two techniques don't agree. They don't produce the same results. They don't give the same position for the same point. And the theory was that mountains might be deflecting the plumb bobs. And this was actually why the Schehallien experiment was proposed by Neville Maskelyne. You use non-magnetic weights, you isolate them from air currents, you do the experiment on one side of the mountain, measure the deflection, then you do it on the other side of the mountain and measure the deflection. And if the deflections both point to the mountain, which they did, then you can determine that the mountain is deflecting the plumb bob from vertical. Sorry, my mouse is misbehaving a little bit. So yeah, this was addressed in some detail by a guy by the name of Archdeacon John Pratt during the Great Trigonometrical Survey of India. And he noted that for the distance between Kalyana and Kalinpur, from celestial observations, the difference should be 5 degrees, 23 minutes, 37 or so arc seconds. But from surveying, it was 5 degrees, 23 minutes, 42.3. So a difference of about 5.2 arc seconds. So which of these, so we already thought that maybe there was deflection of the plumb bob. Could we actually confirm this? And it turned out that we could. What he did was he took a line that was 7 miles long, and he propagated it 500 kilometers. And he developed, in the propagation of both of the endpoints of the line, introduced an error of 0.002%, or about 7 inches, across several hundred miles, which told him that his surveying results were extremely accurate, and therefore it must be the azimuthal calculations. That's that's the conclusion that we've come to, is that azimuthal, here's an azimuthal sector, which is a sort of astronomical tool for looking straight up. But this is deflected because the gravitational field is not orthogonal straight down. It doesn't go it's offset. And a way of looking at this from side on is that the plumb line is always normal to the geoid, to the equipotential surface, whereas whereas we might kind of expect it to be orthogonal to the reference ellipsoid, but it's not orthogonal to the reference ellipsoid. It's not orthogonal to the surface of the planet. It's normal to the equipotential surface. And this is what this phenomenon in surveying is called vertical deflection. And it's studied quite extensively. So by the end of the 19th century, we were starting to observe gravity with high precision, but the question then became, might it actually be useful? And a guy by the name of Laurent Yotwash developed this balance for detecting gravity gradients. And in 1918, he was able to prove the concept that you could use these gravity gradients to detect subsurface oil deposits. This technology was brought across to the US in the early 1920s after the end of the First World War, and was used to find the Nash oil dome in 1924. So this is a technique that we've had available to us for mineral exploration for over 100 years. On the left-hand side there, you can see the map that was made of the salt dome underneath the, which was trapping the oil. It's worth noting the units here. 1 yacht wash is about 10 to the minus 9 meters per second squared per meter. So that drops out to 10 to the minus 9 per second squared, which gets even more complicated. And this is a technique we're still using today. Here's an example from Brazil, where they take gravimeters, those black dots on this figure, points where they've taken gravity measurements, and they've mapped the gravitational acceleration. In this case, a gal is 1 centimeter per second squared. So a milligal is 10 to the minus 5 meters per second squared. So this is a real world application. We still use it today. We use slightly different versions. We tend to use gravity gradients more often. Are there any other real world applications for gravity? And it turns out that there are, and one of the most sort of secret of them was submarine navigation. So normally in friendly waters, you can use a fathometer. You can use basically a sonar that will send out a pulse of sound that will bounce off the object and tell you where there's any tell you where there's any obstructions. But if you're in hostile waters, sending out sonar pulses is extremely undesirable. You're telling everybody where you are and what you're up to. So the military wanted a way of avoiding that if they could. Now, it turned out that we've been doing this for 100 years as well. A chap by the name of Venning Meynish, a Dutch geophysicist, was using submarines to make gravity measurements. That's him in the top left. That's his instrument, which used pendulum observations. And there's a map that he made of the area around the Sunda Sea, west of Papua and south of Indonesia. So that Andaman and Sunda Sea area. So he started doing that in 1923. So again, this is something we have been making gravity observations from submarines for more than 100 years. Now, in the first instance, what the submariners would do is they would measure the strength of gravity and compare that to a gravity map. And then they could sort of work out where they were on the gravity map. This was combined, and still is combined, with inertial navigation systems. So an inertial navigation system records all of the accelerations that are applied to the submarine and then tells you, okay, we know where we started, we know what the accelerations are since we started, therefore we're here. They have various drift problems and various propagation errors involved with them, so they're not absolutely accurate. And so it's very good to be able to double check against gravity anomaly maps like this. But more recently, submarines use what are called as gravity gradients. So the second derivative of the gravitational acceleration. And these have diagnostic patterns, so you can recognize where a mountain or or an obstruction might be relative to the submarine, based on the gravitational signal. And this is in more recent times. This has been released to the public. Actually, now mineral exploration companies use gravity gradient observations. So it might be useful to have a look at some of the different techniques we use for measuring gravitation. This is the Lacoste FG5X. It's one of the most accurate absolute gravimeters available today. An absolute gravimeter is a drop gravimeter, so you drop an item and you measure how long it takes to fall, and then you lift it up and you drop it again. So it provides a single point in time observation. Now that you can see the color photo top right. That shiny cylinder is the drop cylinder. Just below that is the laser interferometer, and just below that is a servo coil, which we'll get into in just a little bit. The servo coil serves as a suspension. So if there's a vibration that might move the instrument, that is detected, and actuators are used to move the reflection mirror to adjust so that it stays in the same position, so that it isn't affected by the movement of the instrument. There are pressure controls and pressure and temperature controls inside the instrument. This instrument is so accurate. Here's a look at its innards. Now, on the right, you can see, on the top right, you can see the corner cube reflector. Now, as it goes down, it's inside a carriage, and that carriage is laser controlled, and it keeps a distance, it keeps a separation of 3 millimeters from the corner cube. So it is on rails, and it gets moved down ahead by a motor ahead of the corner cube. Just below that, you can see the super spring, and on top of that, the interferometer. The interferometer is bouncing a laser off the corner cube as it falls down. Now, as that carriage falls down, there are actually counterweights that move up, so that the center of balance and so that there's no mechanical rocking, so that the motion of the drop of the corner cube downwards is compensated by an upward motion on the side carts. This is a highly precise instrument. The drop chamber is 20 centimeters long, is 20 centimeters tall. So it drops the corner cube a distance of 20 centimeters. This instrument is sensitive enough that it knows that gravity is not constant inside the drop chamber. So it can detect the fact that gravity at the top of the drop chamber is different from gravity at the bottom of the drop chamber.
I have a question.
Yep.
How is there's an interferometer? How is that interferometer doing the measuring?
So it's firing up a beam which hits the retroreflector, which comes down, and then it hits on the downward part. So it goes through a one-way mirror. So it goes up through the mirror, hits the corner cube, comes back down, gets reflected off to the side. And so these laser pulses, which are fired one after the other, their results are recorded off to the side. Is that clear, or? Okay. Another modern development is cold atom gravimetry. this is actually quite exciting now. What this is based on is you laser cool atoms, so you get a cloud of rubidium or strontium. They turn out to have the best sort of atomic structure for this type of exercise, and you cool them with lasers. That sounds a bit non-intuitive, counterintuitive. But what happens is that the laser is tuned so that it will take momentum away from atoms that are moving towards it. So you pump this laser at the atoms, and any atoms that are going towards it get slowed down. And so basically you're slowing down the entire cloud of atoms. This is, if you look across to the left and off to the right, you'll see this thing called MOT. That's the magneto-optical trap. So that's where these lasers are supercooling these. And the point is to put the cloud of atoms into what's known as a Bose-Einstein condensate, so that all of the atoms in this cloud share the same they share the same quantum state. And that is important because the propagation of the atoms is now governed by Schrodinger's equations. And so what happens is you push the condensate into the chamber, you split it into an upgoing, or if you look at this thing at the bottom right, the atoms come in from the left, they get split into upwards and downwards propagating clouds. They get zapped again so that their path is reversed, and then you recombine them. And once you've done that, you can look at the interference pattern between the two. Here's one that's actually, the previous one was designed for space missions. This is one that's designed for use on Earth. And the interference pattern we're looking at here is that the 3p0 and the 1s0. So they're the electron transition populations tell us using we can retrofit using Schrodinger's equation to tell us what the strength of gravity was. These are new instruments. They used to be quite big and quite cumbersome, but they're lowering inside. Now there are multiple groups that are planning to put them into space. They're becoming more and more viable. This is a supercool, a superconducting gravimeter. So this is the central piece is this bit on the right. So you've got a niobium sphere, and it is surrounded by superconducting coils. If any acceleration acts on the niobium sphere, it will induce a current in the coils that will push it back to it, that will keep it in its initial position. So it's trapped in here, but by monitoring the electric current that goes through the coils, you can reconstruct the accelerations that have been applied to the ball. These things are stationary. They need to be very stable. I help maintain our university's superconducting gravimeter. They're extremely sensitive, and sort of even walking into the room, that you need to stay out of the room that they're in. You need to try and isolate them. Even the vibrations of walking next door are detectable. These things also, they detect changes in air pressure because the mass of the overlying air changes. They detect tidal signals. They're extremely sensitive instruments. Going back to our mineral application, one of the mineral exploration techniques is to put a gravimeter down a borehole. And in this particular example, they've put water. They've let the signal of water at a particular depth grow. So they've pumped water into the ground, and they've done observations here as they lower the gravimeter down the borehole. So this is a technique that can be used to determine the depth at which a gravity anomaly occurs. This is a series of increasingly sophisticated airborne or mobile gravimeters. Where these are commercial, these are again commercial applications. Again with micro G Lacoste and Lacoste Romberg. You may remember that the Lacoste FG5X was the one that I was discussing earlier. Lacoste and Romberg actually made significant progress towards developing the first effective spring gravimeter, but those are kind of redundant now. Here's another mobile developed by Lockheed Martin. It actually rotates the plate with the accelerometers in it. Rotates, and they're able to sort of algebraically derive acceleration. And here's another commercial one. This one is more for shipborne calculations. Here are just some images of these systems in deployment. You can put them on boats. You need them thermostabilized and gyrostabilized if you can manage it. And these shipborne gravimetry missions are actually quite important for sort of normalizing the results that I'm going to be discussing in just a minute. Going back to real world examples, it turns out that we actually use gravity to map the ocean floor. If you've got a satellite altimeter that's flying over the ocean, the presence of a mountain underneath the ocean implies gravitational influence to the water, and so the water over the mountain is actually higher than it is over the lower surrounding area. And conversely, the water over a trough or depression will be lower. As your satellite flies over, it sends down signals, gets back signals, and it can easily detect these. Now, should we take those at face value? Well, actually, we put a significant amount of effort into cross-checking our satellite altimetry with tide gauges and with shipborne instruments, because there could be an offset, there could be some sort of bias, and we want to detect all of these various effects. People talk about sea level as though it's a very simple thing to analyze and as though the sea surface is very flat. But you can see here that sea surface height actually has a number of things. It's influenced by the weather, it's influenced by wave climate, it's influenced by the gravitational field, and you're trying to get a mean sea surface, whereas what you're sampling is an instantaneous sea surface. So you need to be very meticulous in how you approach this in order to get results that are meaningful. For tide gauges, just there are a number of different styles. The most simple is a tide staff, which is basically just a ruler that stands there, and you look at the ruler and see where the water level is. Nowadays, you've got what we see on the right, which is a range sensor. So you've got some tube that's isolated from the atmosphere that just uses ultrasound or radar to work out how high the water is in the tube. In between, you've got float style things that will move up and down with the water level. You've also got water pressure and temperature sensors so that you can, because thermal expansion is one of the things that changes water height, you need to, and tides and currents and dynamics, you kind of need as much information as you can. And you also need wind and air temperature in order to fully understand the dynamics of the system. Now, ideally, what happens is that you've got a co-located GPS system or some other global navigation satellite system, and every once in a while you want to send out a gravimeter and just check what you're doing. Get out of the way. Here, for instance, is a tide gauge record for Lake Erie. Well, actually, this one's Lake Superior. Sorry, but they did it for all of the Great Lakes. The solid black line is the tide gauge, and the crosses are the Topex Poseidon altimetry. And the open triangles are the Jason satellite system. So this shows sort of cross and intercomparison between the various forms of measurement that we've got. These are just some examples of some seaborne missions that have been gone out. And I think it's interesting in the next figure. If you look at the sea surface height that the buoy has, the buoy, I know you Americans are very fond of the pronunciation buoy, but if you're going to do that, you have to say that people are buoyant and that it's a buoyancy force. And if you're not going to say that, just say that they're buoys, it's buoyancy, and people are buoyant. Okay, give it up.
But we do it's a buoy and it's buoyant.
Yes.
That's yep.
Well, given that they're related words, I think you're making life difficult for everybody. Okay. But if you look at the figure on the left here, well, either of these figures, you can see that this buoy is 20 meters above the reference ellipsoid. So it's 20 meters above zero altitude, 20 meters above what you might call basic sea level, if that term even means anything. And this is with GPS measurements. And it's cross compared with sea surface height measured by the satellite overpasses. So here, for instance, so this is sea surface height. This is mean sea surface height. Now, this is closely related to gravity, but it's not actually gravity. And the reason for that is because there are dynamic influences. In particular, if you look at the Western Pacific, you can see that temperature seems to be, the sea surface seems to be quite a bit higher there than it does. And these are in meters, so these are quite large deviations. The lowest sea level is around the south of India, which I constantly talk about, but the highest is only about 85 meters. And there are a couple of points that get up there. But because the Earth is rotating to the east, that means that from inertia, there is what is called western boundary current intensification. So the water actually tends to pile up on the western side of large oceans. And this leads to western currents. One of the most famous would be the Gulf Stream, in fact. That Gulf Stream is driven in part by Coriolis forcing or rotation towards the right. So the water's inertia sort of carries it up to the left. It doesn't show up entirely well on this scale, but if you zero in, you can see that it turns up as a sea surface. Now, from the sea surface height, we can infer the ocean floor topography. So we can work out from bulges and valleys in the sea surface. We can identify, and this is one such identification. So we take our sea surface altimetry, we apply the law of gravity to infer what the ocean floor looks like, and then we can check it. And you can see this process yourself if you go to Google Earth. If you just go over the oceans, you can dimly see them in the figure on the left, but if you zoom in, you can see on the right that there are what look like these straight snail trails, like these straight arcs, or these straight lines, where you've got much higher resolution than you do elsewhere. The things look a bit sort of muddy, and then you've got these tracks that are sort of crinkled up and look very high definition. That's because those are ocean bathymetry missions. So for instance, on the left, we've got this portion of the Southern Indian Ocean, which had only a few sonar soundings. And then MH370, if you remember the missing airline flight MH370 went missing, and a bunch of sonar missions were sent out to go look for it. So on the left is before the sonar missions, and on the right is after the sonar missions. So the left is primarily gravity with a little bit of sonar. On the right is a lot of sonar combined with the gravity. And you can see that the image on the left is kind of just an out of focus version of the image on the right, which is to say, to get the detail, you really want to be doing sonar. But the image on the left is not actually wrong. It's not egregious in any sense. It captures most of the major features. It captures the rise on the right. It captures the higher ocean floor on the left even, and it captures the flat bit. So it captures most of the details. It's just out of focus. This actually is a little bit out of date because now there's a new mission that's come online, the SWAT mission, which was launched in the last few months, and it's just started to produce data, and the data is extremely high resolution. So we're going to be able to get much better than we used to from the ocean surface. The SWAT mission stands for Surface, Water and Ocean Topography. So it's specifically out to detect this sort of thing. So now we're sort of returning to measuring gravity. It was sort of worked out early on that one of the ways you could tell about Earth's gravity field was basically by putting disco balls in orbit and bouncing lasers off them. So this is called satellite laser ranging. There are multiple missions. LARES, AGISAI is the French one. Stellar and Starlet, I think, are American. Ettalon, I think, is Russian, but these are still ongoing. These are basically unpowered, so they're at the mercy of gravity, and you just fire lasers at them to work out where they are, and use their propagation to reconstruct gravity. There was an early mission. I say early. 2004 is about the blossoming of this with Champ and Goche. Goche, I've looked at in some detail. It has onboard gravity gradiometers, but the state of the art at the moment is the GRACE mission and the GRACE follow-on mission. This consists of 2 satellites, which are in low Earth orbit. They start out at an altitude of about 500 kilometers. They eventually descend to about 350 kilometers before they stop working. These 2 satellites, which are as identical as we can make them, fire a laser backwards and forwards between them. This for GRACE, it was K-band. For the GRACE follow-on, they also had a laser interferometer. The central idea is that as the the satellites are going along, the lead satellite gets pulled by a positive mass anomaly. The second satellite sort of lags behind, and then once it's past the anomaly, the second satellite catches up. So just to show, in this case, I've got the 2 satellites coming in from the left. As they come in, the lead satellite gets further away from the following satellite. We've also got GPS positions for both of these satellites that we use in this analysis. But once it gets past the mass anomaly, the lead satellite starts being pulled backwards. Meanwhile, the rear satellite catches up. And then the rear satellite is once both are past the mass anomaly, the rear satellite is still more strongly affected by the mass anomaly. So it gets pulled backwards, and the lead satellite sort of gets to go away and gets to increase. So we're looking at intersatellite ranges, or more specifically range rates are what are used. But we can use them to derive the gravity field, which we've done here. We can also extract what's called the temporal gravity field, which are, this is an example. This is 2 examples, actually. On the left is from 2013, from May, and on the right is from January 2016, so towards the end of the GRACE mission. Now, one of the things to notice about, obviously, the top figures are incredibly stripy. And this is because most inversions use the range rate. The range rates are closely correlated in north-south. So it's very hard to tell the mass elements apart based on the observations. And so in this particular paper, they've done some filtering in order to get rid of that. But that's not how my group does it. Actually, we developed a new technique that actually uses range accelerations. And the range accelerations turn out to be much less correlated. So they're much more localized. The range accelerations are only non-zero right over the mass element. So it's much easier to get separation. So we don't have to do any of this filtering or correction or that sort of thing. It took us about 8 years to get this into print. We've had results for 8 years, but every time we tried to publish, we got told by the reviewers that that's not how this is done, and it is impossible to use range accelerations. So we were in fact subject to the exact bias that the flat earthers claim exists, and we had to get sort of the head of mission to visit us to actually check that, and he was able to replicate our results. So he looked at what we were doing, went back to his place, did range acceleration inversions, and said, yeah, it works exactly as they said it did. So so we felt quite gratified. But the one thing I do want to point out is actually that red thing over North America. That red blob over North America, which shows that in this case, that means that North America, Canada, is gaining mass. And that is actually as a result of glacial isostatic adjustment. That is actually a result of, because there was a large ice sheet over there that was pushing the surface down. Find the company rather boring, do you, Michael? Just stifling a yawn there, but anyway.
It's a marathon for me here.
Yeah,
I'm nearing the end, so no, it's not
okay.
not you.
So the 20,000 years ago, there were large ice sheets over North America. You know, the North American ice sheet extended from the east coast to the west coast, covered most of Canada, and was, you know, up to 4 kilometers thick in places. And this pushed a lot of mantle material away from underneath, and that mantle material is still flowing back. That's what that red signal is under North America. And you'll see a similar red signal under Scandinavia on the left-hand side of the figure. And that's the same thing because of the Scandinavian ice sheet pushed stuff away. So my PhD thesis was dedicated to modeling glacial isostatic adjustment. And so this is largely how I sort of drifted into gravimetry and satellite gravimetry, because this is for the satellite gravimetry people, this is noise, and they would really like it to go away. And can we just model it properly? Which is easier said than done. I did have a few animations that I wanted to show people, but that's the end of my basic presentation.
Yeah, some animations would be great. Are they
Okay.
Yeah,
All right. So I'll just have to reshare. Okay, so this is these are GRACE solutions for Antarctica and Greenland. So this is mass anomalies. Blue means mass gain, red means mass loss, and we'll just play it through. This is a short one, takes less than a minute. So our time series starts in 2002, 2003, and here you can see the mass loss in West Antarctica, some of it in Thwaites Glacier, little mass increase inland, which we think is from precipitation. For Greenland, it's all mass loss. We're about to come up to the gap between GRACE and GRACE follow-on, which lasts about 2 years, and then GRACE follow-on comes back online. And these are the modern. So these are the time series we can get, and this is the sensitivity that we can have with this instrument that we can see this. I've got another animation, if that's okay.
Yeah.
This one's quite good, I think. Unfortunately, there's one I have in my office, but I can't get to it over the holidays. Just a second. What are we doing? Okay. So this is a somewhat longer one. So I'll go through it at double speed. Okay, so these are mass loss signals. This is Australia at the start in 2004, and you can see green is basically zero. So as at 2004, you can see over the period 2004. I think this goes to 2009, not entirely certain. Australia is losing a lot of mass. This is the centennial drought. Similarly, here in Central California, it's that Central Valley that we're looking at. Mass loss here at the beginning of the 21st century. This drought was a major event. Actually had some effect on uplift rates in California. And certainly ultimately led to some devastatingly intense forest fires. The Middle East, we do have global solutions, but these are just sort of some regions of interest that we're looking at. You can see trends of mass loss. I think the next one is probably going to be the most interesting in terms of showing this instrument's sensitivity, because it's going to capture this is the Indian subcontinent. And here we're going to be able to see seasonal variations. For the other regions, the seasonal variations aren't that large. But here, the seasonal variations are of sufficient amplitude that we can pick them up, even against the background signal. If you looked in detail at the Australian time series or the other time series, you'd be able to see the seasonal signal, but in terms of the overall mass loss, it just gets masked. So here you can see the monsoon signals change, and of the sorry, I'll get rid of that. Of the of most concern is that the pattern for the pattern of changes, the pattern of the monsoons is changing. In other words, it's no longer the same, which is something of a concern. India has something like 16% of the world's population, but receives only 4% of the world's fresh water. So any changes to sort of monsoonal patterns and freshwater ground flow are actually of major concern. The Indian government are particularly concerned about it with good reason. Now, I do have a presentation on glacial isostatic adjustment, that thing that I ended the other one on, if you wanted more from me, or if people fall asleep from too much of my voice. So
I think what you've covered is a good amount for this presentation. And so to be clear, you said it, but I think to just make it more clear, a lot of this change that you were showing in that last segment was due to lack of water.
Yes.
Right?
Yeah.
So water is rather dense, and if there's less water, then there's less
gravitational signal, and the satellites are these measurements turn out to be sensitive enough to catch. The animation that's locked in my office, unfortunately, is actually quite beautiful because we can follow a flood. It shows the floodwaters in sort of northern Australia in 2010, 2011. And you can see these floodwaters accumulating in the centre of Queensland and then flowing down the rivers and out to the coast. And you can detect their gravitational signal in the data. So this is the level of sensitivity that we're getting to with our gravitational observations, that we can use it to track rainfall, soil moisture, that sort of thing.
All right. So then, obviously, if the water leaves that area, it goes somewhere else. Where is it going to?
So most of it's ending up in the ocean. So the predominant there are multiple contributions to increasing sea level. The dominant one is actually thermal. So it's thermal expansion of the upper layers of the ocean. There's also water coming in from Greenland, from the melting of ice sheets and glaciers, predominantly Greenland, but also West Antarctica. But actually, human extraction of groundwater turns out to be a serious contributor. And in fact, it's so large that it has affected Earth's rotation. So the pumping out of groundwater by humans using and then flushing it into the oceans has changed the path of true polar wander. So at around shortly after the year 2000, we were tracking Earth's true polar wander, and all of a sudden it sort of deviated. It did a really sharp turn. And that sharp turn we now understand to be caused by human pumping of groundwater into the oceans.
So, and a lot of that then is wells, right? That's what this is.
Yeah. So a lot of that is just human usage in various forms. So pumping out aquifers and wells, in essence.
Yeah, and yeah, when you bring water up from the ground, it winds up in streams and rivers, which eventually finds their way to oceans if they don't evaporate. But of course, if they evaporate, then it's precipitation, which winds up in oceans.
Exactly. Yes.
So, so I ran a half marathon a few years ago to help build wells in villages in Africa, which ironically then contributes to that happening.
Well, I mean, it's sort of a. I don't consider Africa to sort of be one of the major sinners in this regard. They clearly need water to be able to live. So, I don't. Actually, we're working on a paper on this just at the moment. In some regions, actually, the influence of this gets really complicated really quickly. The influencers are going to find out that they're not that safe.
It does get complicated.
But just to answer some questions, I don't work for a company. I work for a university. My position is funded by a company. But...
All right. Well, we'll do in a minute. We'll do some Q&A. But for the podcast, thank you very much for joining in the podcast. PhD Tony, I will put the link to your YouTube channel in the podcast description. Anything else before we wrap up the podcast?
No, thank you for having me on, and I hope I didn't say too often. It is still a noise that I make a lot. I am aware, but I hope it was at least somewhat tolerable.
All right. Well, thank you very much, and we'll see you next time on the Toon Show.
Thank you.
All right. Well, that ends the recording portion of the Toon Show. So let me do this. All right. Well, we do have some questions from the audience that I thought would be good to field here. So we've got, let's see, does the topology, Orb Ital says, does the topology of a region affect fresh water availability?
Topography of a
topography,
yeah. It kind of it can. So in very steep-sided areas, your opportunities to catch groundwater might not be so great. So your opportunities to interrupt water flow do depend on topographic nature, and certainly the hydrological aspects, so the existence of aquifers and subsurface water flow also depend very much on topographic features, but also geological features like the permeability of the various layers and that sort of thing.
All right. Have you ever been, Zone Television asks, have you ever been approached by SpaceX, or would you consider working for them?
I have never been approached by SpaceX. They would have to. I don't think that they have any need of my expertise. I'm a gravity theorist. I'm not a rocket scientist. I'm not a designer of satellites at all. That having been said, I have severe problems with SpaceX's business model. I don't consider it sustainable, and I don't consider Elon Musk a particularly constructive presence in technology or science fields.
Right. Mallory early on said, may not understand, but this is satisfying to hear.
Okay, well, I think Mallory and I had a good time discussing the ramifications of rim velocity on one of your streams. And I think I'm finally begin. She and I are finally beginning to get on the same wavelength. So,
Um, let's see. We've got Monkey Cat Pat Pat said, one of my favorite activities, falling asleep, listening to PhD Tony's sweet, sweet education. All right. Icy Spin says, what's the importance of having multiple satellites?
well, the importance of having multiple satellites is that you can sample well, for Grace, you need multiple satellites because it's inter-satellite ranges that's important. But in general, multiple satellites help you sample the Earth, sample a particular point on Earth more frequently, so you get better time resolution, and that otherwise you have to wait until your satellite gets back over the point. Depending on the type of satellite, some satellites are designed to repeat the same tracks over and over again, and they'll just sample those tracks. And other satellites, sort of like the Grace satellites, sort of are in a polar orbit that slowly sort of goes around, and you get fairly good coverage over the course of a month. We're trying to get that down, but the shorter the period, the larger the gaps between the ground tracks, and so the less resolution you have.
So I suppose if you had multiple Grace satellite combinations going simultaneously, that would help.
Yes, that's right.
Have...
And yeah, there is a proposal to do that, and so the NASA are working on another Grace style, and the Europeans are working on that, but they're also working towards another one. And they want to put it in what's called a bender configuration. So the Grace satellite is in a polar orbit. The bender configuration will have some form of obliquity. And sort of that striping that I showed you, that north-south correlation, if you've got a satellite that's at an angle, it'll help break that correlation. So it'll help achieve a higher resolution.
Yeah, because it's getting it's varying where it's going, right? If it's polar, it'll tend to be a bit repetitive, especially over the poles.
Yeah,
you get a lot of resolution of the poles, which may be great if you really wanted that.
Yeah,
but and then less over the equator.
Yes, that's right, and you get a higher sampling at the poles, wherever that is, for your chosen orbit. But yeah, it's a it's a trade-off. if you do it obliquely, you're not sampling the poles at all. There's a maximum latitude beyond which you can't get. It's, but most of the areas that we're interested in exploring for minerals or whose water use we're interested in are actually at low latitudes anyway. So
Yeah, not over the poles. All right, so let's see.
somebody picked an argument with me over SpaceX. The reason I'm skeptical about SpaceX's business model is that one of their proposed businesses is suborbital intercontinental transports. I don't see that as being viable at all.
Yeah, the idea that they would take off and land using a rocket ship to get across, different.
You can make the journey. You can make the journey so much faster. Fine. All you need to do is emit as much carbon dioxide as 40 airplanes doing the same journey. So you're not actually helping in terms of greenhouse gases. And if your claim is, well, we can make multiple journeys in a day, well, that's great. How many people actually need to make these intercontinental journeys? Is there a market for 10 of these for 10 flights a day from San Francisco to Dubai and back? If not, then what are you doing? You're not actually bringing any value to it. And the other thing is that there's no infrastructure for this. There's no rocket landing area near downtown Los Angeles, nor near Dubai. And given SpaceX's safety record, I don't see them getting one anywhere near high density areas. So even if your air journey only takes 40 minutes, you could be looking at hours of rail journey to actually get to your hotel or anywhere you want to go. So
here's one thing. The new rocket is using methane instead of kerosene, essentially, and one of the reasons why is for Mars.
Yep.
Because they can manufacture it on Mars, and to manufacture it, they need to, as I understand, they need to bring hydrogen with, and then they can use carbon dioxide.
I thought they were trying to get hydrogen from the water
on Mars.
Yeah, I think their aim was to get subsurface water deposits and liberate the water there. But I'm not actually 100% on the details. But I don't consider the Mars idea particularly well thought out, and certainly the timeline isn't realistic.
Well, yeah, he's a bit of a timeline fudger. So the specifics of the chemistry here that I was wondering about. So whether you bring the hydrogen with or you extract it from water, in order to make methane, then you need carbon, and you get that from carbon dioxide. So that will then remove carbon dioxide from the environment of Mars. Now, I could, rather than using whatever process to get the methane that they're doing now, could they use a similar process to convert carbon dioxide to methane? And then it's a wash, potentially, I don't know, about how much carbon dioxide is being liberated in a rocket launch.
Well, except that you're not getting the carbon dioxide out of the atmosphere for free. You're investing energy in that.
And what does SpaceX or Musk also own? They make solar panels.
Yeah. Though I don't think that's a hugely successful portion of his business.
Well, yeah,
This is the thing that I think is misunderstood a lot about Musk. He's not actually an environmentalist. in any sense. He's a profiteer. And he's in electric. The only thing on the Tesla that Musk designed was the recharge port, so that he could patent it, so that other car designers would have to pay him to recharge at Tesla power stations. Then he goes around the world getting local governments to pay to build Tesla power stations, so that he's got other electric car manufacturers in a vice. That's his entire business model. And this whole, he's not really he's in this for altruistic reasons. He's not in anything. He's not into anything for altruistic.
I wasn't saying that. I was thinking about the model of using Starship to transport people point to point on the Earth, and your main, at least your first issue you had with it was the liberation of carbon dioxide. So
yes,
I was thinking, could that be an offset to it?
Not realistically, no. There's no sort of, in order to get carbon dioxide out of the atmosphere, you need to invest a lot of energy in doing it.
Yeah.
And it's just not worthwhile at this point. And there are arguments about it anyway, in the sense that if you pull carbon dioxide out of the atmosphere, then actually carbon dioxide will be liberated from the oceans. There's carbon dioxide that is only absorbed in the oceans because the carbon dioxide partial pressure in the atmosphere is so high. If you start pulling that out, it's going to undissolve from the oceans. Because you're lowering the partial pressure, so you're sort of, it's a Sisyphean task. You're better off just not omitting the carbon dioxide. I will take the opportunity to lay the boot into Thunderfoot here, because he did a series of
I have not seen those
on climate change, and he concluded that sulfate aerosols were the one thing that has been demonstrated humans are capable of producing. They're capable of putting into the atmosphere, blah, blah, blah. Yes, and that would be wonderful as long as we're happy living without an ozone layer. Because sulfate particles turn out to be a catalyst for the decomposition of ozone. So if you want to pump sulfate aerosols into the atmosphere, be aware that it comes at a significant price. We just got this under control. We're just sort of sorting out our ozone problems. And now Thunderfoot is, it would have been okay if he'd mentioned that this is a drawback with this technology, but he didn't even discuss it. And it's a well-known shortcoming of this proposed geoengineering trajectory. So I kind of think that
Thunderfoot was proposing putting
sulfate aerosols into the atmosphere to cool the Earth.
Oh, to cool it, to counteract warming, not to directly affect the increase in carbon dioxide, but to
to use sulfate aerosols to basically absorb or reflect incoming sunlight.
Oh, okay.
Basically you're stopping energy from reaching the surface of the Earth, so it can't be trapped by the carbon dioxide.
That type of thing of reflecting the light does sound like just a bad idea, no matter how it's done. Just
it sounds
from an entry level, yeah.
It sounds like something you really want to be sure you know what you're doing.
Yeah, I've heard people talk about putting things in space to reflect light.
You have to have an ironclad grip on the physics and the ramifications, which is why, sort of pointing out that it would actually destroy the ozone layer is something that we need to consider. Anyway.
Yeah. So there's a book I read quite a few years ago called Rings of Ice by Piers Anthony. And
Hmm.
in this book, the this is part of this. I was young when I read this. It was part of my uh, big resistance to just this idea at all. That
Hmm.
they in this book, scientists and the world's governments had gotten some ice from space from somewhere. They found asteroid belt or something. They brought the ice to the Earth to act as a reflection, but they didn't
Yep.
quite get it right. And instead, this huge amount of ice from space fell into the Earth and flooded the Earth until it
Yeah.
basically turned into that Kevin Costner movie Waterworld.
So, well, you've brought in a lot of water at that point.
Yes.
But yeah, it's the uh, it is one of those but it is one of those issues where, you know, if you're thinking of making some intervention, you need to be certain that you're getting it right, that you're not actually making a rod for your own back. And I don't think that I think that, you know, I think that Thunderfoot presenting this as, well, it's obvious this is what we need to do, I think sort of it was a bit facile. Um, he needed to uh, be more thoughtful in how he approached this. So he would call out somebody else if he saw somebody else do that. I'm calling out him because I saw him do that. So
Take that,
yeah,
Thunderfoot. Bring it
yeah,
here.
yeah. I'm sure he really cares what I think. Um,
Uh,
but
all right, we've got some more questions here. Professor Parks says, Tony, do you know how many satellites currently in orbit are used in geophysics?
I know quite a few. My group alone uses ISAT-2, Cryosat, SWAT. Um, there's another one, uh, SMOW or something, soil, moisture, ocean, water. There are buckets of them. The uh, Grace, Goche, like there are quite a few.
Okay. Monkey Cat
I don't have
okay,
a that's as precise a bucket load. That's as precise an answer as I have for him.
buckets. There you go.
Yes.
Monkey Cat Pat Pat says, PhD Tony, if you could pick three flat earthers to send to space, who would you pick?
Um, for the purposes of convincing them that the Earth is a sphere, or for the
Well,
purposes of
there's two obvious questions. Depending on the purpose. Yeah. Well, in
are
one
they
they get to
coming back?
that's the delineation. So I guess you can pick six flirts then, three for each.
Okay,
Oh, he said one way trip. But
one way trip.
but let's expand it. Let's yeah give
All right. All right. If I were to pick three flirts to send into space, not to come back, it would be Quantum Eraser, Santos, and it's tight for that third spot. And there are a lot of candidates out there, but let's say Eric Dubay.
excellent
Um,
choices.
if to go up and come back, I pick Dan the Waterman because I think he would be convinced by that. Um, I would. Who else would I pick? Jeranism. And what's the name of that guy from California you were talking to? The he's sort of the head moderator of the Flat Earth Discord channel, whatever it is.
The Flat Earth Discord channel?
Yeah, there's a Flat Earth Discord that I was on, and that you went on a couple of times.
The Asylum?
Yeah, the Asylum.
That was man, I'm forgetting his name now.
Anyway, him.
Yeah.
Or Radblade, actually. Let's change it. Radblade.
I would pick for those that come back, I would pick those that are most likely to have the biggest sway.
Mm-hmm.
So yeah, I think Jaren is a good choice. But Sergeant and Jaren, their audiences overlap.
Yeah.
A lot. So yeah, I wouldn't pick Oakley because he has such a tiny audience, and none of them would be convinced. If Oakley switched tomorrow, none of them would join him.
I don't have any expectation of Oakley to be honest about anything. So,
if he didn't see how he could make more gold pressed latinum from it, he wouldn't do it.
Mm-hmm.
Yes. Shane St. Pierre, no, he's
no, I wouldn't send Shane St. Pierre.
He doesn't have anybody's ear. I suppose you could do one of the Religiflurfs that have a big Religiflurf background, like Odal. Ugh, gross.
No, I wouldn't send any of them. Like this is the thing. I'm not basing mine on who I think has an audience. I'm basing mine on flirfs I think will be honest about their experience.
That's a different purpose then, right?
But it's no point sending up somebody who's just going to lie about what they experienced. If they, regardless of how big an audience they have or small an audience they have. So it's my first criterion. If you send up somebody with a big audience, but they just come back and lie, pointless.
Yeah.
So yeah.
Icy Spin. What about the guy's channel that got shut down? His name escapes me. Santos? Santos?
I think he's currently playing a role in radioactive waste disposal experiments.
Yeah. All right. Cretan Bull says SpaceX could not exist without government funding. It's another example of privatizing public money for private profit.
Well, I think that's a business model that that Elon uses a lot. Is siphoning up as much public money as he can get. It's true of Tesla. It's true of SpaceX. It's true of it's true of a lot of his stuff. It's just.
Well, he's not alone in that, of course.
He's not alone in that. No.
But, yeah.
But he will hypocritically claim that it is something that he is fervently opposed to. But he takes advantage of it. Everybody. Professor Parks says that he would pick Whitsitt. I don't. Professor Parks has a very high opinion of Whitsitt's honesty. I don't.
Whitsitt can't do anything else, and he knows he can't do anything else. This is he made a permanent decision. When he he did how public he is, he can't go get another job. They'll Google his name and say, "Oh, no thanks." Unless it's a low grade thing. If you're gonna send him on a one-way trip, you could pick Caleb, because he's gone full late 30s Germany on us.
Yeah, well, he was up there. I just haven't had any personal experience of him.
Yeah.
So
All right, so we've got Alyssum says swinging by to wish everyone a Merry Christmas and Happy New Year. Now that we've had Year of the Sextant, what's your prediction for the new FE claims? Well, the Year of the Sextant was actually
2 years ago.
2021. Last year, or this year, the year that is 2023, I came out with the gravity challenge that has been completely ignored by all flat earthers. So next year is the year of the eclipse. That's what I think. I do intend to do a challenge on that because we know they can't be. You know what they always say. They always say sorrow cycles, or they say Antikythera, or they say Prague, the clock in Prague. But when you ask them, oh, well, show me how it predicts the line of totality. They can't. They run.
Yes, it was extraordinarily funny watching Santos claim that all you need to do is work out where the nodes of the orbit are
by using an ephemeris.
Well, yes, that is how it's done. But that is based on a spherical geometry. So the ancient Greeks dedicated much effort to doing the mathematics on this. Professor Parks he's confessed that he gives Whitsitt a lot of latitude for some reason.
It's weird, Rob. Whitsitt's yeah.
And in our discussion after our debate, Whitsitt intimated some threats at me. He said that, if we were in the same place, I'd be scared and I wouldn't try and convince him of anything, and I wouldn't be telling him what to think or anything like that, which I consider Whitsitt looks like he could break in a strong wind. There's no degree of physical intimidation to Whitsitt. And B, it's infantile in its construction, and I got that was the point where he just, okay, you've lied about my discipline, you've lied about my colleagues. I mean, he was quoting seismologists and earth scientists that I've actually worked with, and misrepresenting their research, and knowing that he was misrepresenting their work. It was, to me, it was one of the most egregious pieces of utter bullshit. And in the same breath, he wasn't listening to what I was saying in the debate. He was typing stuff in the chat.
Yeah. Just last week, I think Caleb on Twitter was quoting Whitsitt's debate with you about Antarctica and how tsunamis don't wrap around, and he actually quoted something that Effie Banjo had put up, and Banjo had an animation of the progress of the wave.
Mm-hmm.
But it was on a Mercator style projection. I don't know if it's Mercator or an Equa rectangular or something, but and so you can't see how it propagates. He just plays that. He's like, look, it's not wrapping around Australia, and I'm like, or Antarctica. I'm like, oh, but wait a second, it's following the coastline of Antarctica, but it's doing it straight across on the Mercator style. And so I took, and I can't animate it, but I took it in Photoshop and I just did a polar projection. And when I do that, it shows the waveform going out in a circle, because on the Mercator projection it didn't. It was skewed, where near Antarctica it was farther, because that map is so skewed, farther away from the epicenter than across near the equator. So when I did that polar projection, it made it circular, and like and I did two of them. I did one when it was, you know, partially out, and another one that I didn't put out there where it was farther out and it was wrapped around and exiting the other side of Antarctica.
I've got I've got one of these as well. Can I share it?
Yeah, yeah.
And actually, uh, this was an illustration that I showed in my debate, and when I wanted to go back and check, which it was no, we don't want to do that. And so this is the South Sandwich Island tsunami. And if we just progress, these white lines are 1 hour isochrones. And so
Yep.
you can see that it's going east and west around Antarctica, and it meets up.
Oh, yeah.
And at the same time, the northward propagating one is only, is still halfway up the coast. Well, it's most of the way up the coast of Africa, but it's nowhere near the North Pole. So we've got this tsunami that has made its way, all the way around Antarctica, so
Where
so this
where is this one from? Let me. I want to.
so this is the. I think if you look for South Sandwich Island,
Okay. And this is from NOAA.
yes,
All right. I'll put that in. That was really nice where it shows yeah, because obviously, and you don't see it on the rectangular map, but
yep,
where they're coming together, they're very clearly wrapping around Antarctica. So yeah, really nice.
yeah. So
All right, let's see if there's any more.
I didn't consider myself equipped necessarily to translate that into a polar projection, but yeah, so the claim that tsunamis don't go around Antarctica, it's rare because mostly they're in, again, the propagating event is in a particular ocean basin, and getting out of there and into one of the other ocean basins is difficult. But if you've got the right propagation event in the right location, you can get into all three ocean basins.
Ideally, can we manufacture? No, we can't manufacture where an earthquake is. If we could, we'd manufacture it to not happen. But if one happened between South America and Antarctica, because that's really that's the choke point.
Well,
if it happen there, then avoid the choke point.
Yeah, so this is this South Sandwich one is just to the east of that gap between South America, it's a but yeah, Whitsett was spouting absolute bullshit, and it was worth noting also in that debate, whenever I wanted to present a counter to his argument, he would just say no, and he would move the conversation on.
Oh yeah.
And it was something that I didn't really spot at the time, but thinking back on it, like he knows he's lying, because you don't do that if you're genuinely interested in what the new data will show. You only do that when you are desperate that the data not not be seen, and stuff not be shown. So he is just exorbitantly mendacious. I consider him one of the most contemptible feeling.
Yeah, and it's him and Nathan Thompson. Those two, when I debated them together, and they cited things and they refused to give the citations. And then after the debate, I'm looking them up. I'm like, these don't work. None of these are support them. They all contradict them. That's when I'm like, wait a second. All Flurf citations contradict the Flurf. That's where I got that. Was
Yeah.
debating him and Thompson. And
Yeah.
so that's why he won't give citations to his thing. See, well, this thing says this. Well, can you link it for us right now? Yeah, I'll get to it. But he never does.
Yeah.
So when I've talked to him, I'm like, link it before you start talking, so that you don't skip linking it later.
Yeah.
Um,
One of the things that I was getting along reasonably well with Dan the Waterman, and he seems not to have internalized our conversations, because I pointed out we have 1 million data sets that all tell us that the Earth is spheroidal. You have one data set which you claim demonstrates that the Earth isn't spheroidal, provided you can eliminate refraction.
yes.
And you say it's up to us to eliminate refraction. No, it's your experiment. You eliminate refraction. You're trying to convince us. We don't have any obligation to convince you. We've got these other data sets that show us what the shape of the Earth is. And I didn't watch his stupid videos, and he just got incredibly hostile when I was discussing it with him on
Discourse
Professor
over.
Park's stream.
Okay.
And he just started attacking me personally, and I left. I've just that's kind of why I think that he's just a complete dickhead. I think he'll be honest if you take him up into if you that's why I sort of nominated him to go into space. But that doesn't change the fact that he's a dickhead.
And it depends when you catch him.
Yeah, it does depend when you catch him.
Which is there's names for that. And
I'm going to give shout outs to Planner Walk and Blue Marble Science in the chat. Good to see them both.
Planner Walk will be in the next stream, as will let's see who. Huge Jars will. That's two. I need at least 3. So Tony, if you're still around, and no others are kicking around. But 4 is even better. I've got a game. I've got a game right here. You can't read it yet. That we will be playing, and it tests your knowledge on a topic that. Well, I'll say that when we played it, because I got that for Christmas when we played it.
Right.
I enjoyed the questions very much.
Okay.
So
Professor Parks is apologizing for Dan being a dickhead on his stream. There's no need for you to apologize, Professor. No need for you to apologize, Rob. You didn't do anything. I don't know if I can call Professor Parks Rob. But I'm going to take the liberty. You didn't do anything wrong. It was entirely Dan's fault. He's responsible for his behavior. I think you're a little gentle on Flurfs. On the other hand, I think I'm an ill-tempered old curmudgeon who flies off the handle regularly. So
a curmudgeon.
Well, that's the least. Oh, prick. Let's say it.
I like curmudgeon. That's great. All right. Let's see. I invited Wolfie, but he's predisposed.
Okay.
Ooh, Leslie wants to play. All right, Leslie. If you're awake for it, yes. And Tony, you can call me Rob, says Professor Parks.
Well, that's very kind of you. Thank you, Rob.
All right. Icy Spin asks, is Mallory the best flat Earth troll of all time or not?
Yes. It's taken me a while to. It's taken me a good time to appreciate the genius of Mallory. But it's undeniable. So yeah, I'm a convert. She and I had a meeting of the minds on your Flurf impersonation um stream.
Um, she- I think she's hilarious.
Yeah,
And I think it's all an act. Does she think the Earth is any? I don't know if she has any clue. I don't think she cares. I think she
I
likes
don't
being a
think she cares.
contrarian.
Yeah, I don't. She is literally one of those people who is in it for the lols.
Yes.
And uh, yeah, uh, as
And
you are, Victoria, there's she's a true artist.
she
Um,
has completely succeeded. When she was talking about the people on her Discord server. She is the center of attention there
yes,
and loves it.
yes.
And you know, it's the entertainment that she provides is certainly worth it. So
Well,
for that,
there's a
yes.
it's sort of basically, I think, anybody who sort of gets up in front of a camera on YouTube has some sort of narcissism element. We do like attention, but uh, but I think Mallory enjoys the attention, but also deserves it. Like, it's a positive experience. Everybody's entertained, and it's all good.
And she
So
puts
I think,
work into it. There's
yeah.
effort there, and yeah, good good for her. Yeah. All right. Well, I'm gonna wrap this one here, and
Okay.
we've got about 7 minutes to the next one, and hopefully that can start a bit closer to on time than I have not been very far back on these. So, but yeah. So Tony, if you're around, oh, we've got okay. Oh, for aviation chat can't fit. Okay, so yeah, so I need somebody that so what do you say? Oh, air scare. Air scare said 45 has 45 minutes, but I need it'd be a little longer than that.
Okay. All
So
right. Well, I'm happy to stay around and
all
play
right.
games.
Well, don't hang up the call when I sign off. So anyway, people, thank you very much for finishing out hour 10 of the marathon. And I am wide awake right now, which isn't unusual. At 2 a.m., I'm usually thinking I should try to get tired soon. So maybe that'll happen, maybe not. But anyway, people, thank you very much. And the next one will be conspiracy trivia, with a bunch of people down under, and Leslie Rohrer in Texas, which is down under Minnesota. Tony, thank you.
Right.
Your presentation, absolutely fantastic. I didn't say that yet. I absolutely loved it. It was super good just to hear you go through all of that. I really appreciate that. So thank you. And
Well,
I'll let you know when it goes out on the Toon Show. I'm going to collect a bunch of them together and just go week by week once I have a backlog. So,
okay. Well, thank you very much for having me on. My pleasure.
all right.
And I hope I wasn't too tedious. I have a tendency to drone on.
Oh,
I
I
like the
loved it.
sound
It
of
was
my own
great.
voice. That's
All right. We'll see you all later. Thank you very much.